You know that feeling, or at least you've seen the videos. The ground, the one thing you count on to be solid, suddenly isn't. But what is actually going on deep inside the Earth when an earthquake hits?
It's a question that takes pretty terrifying human experience and connects it to some of the most powerful forces our planet can dish out. And the answer, well, it doesn't start on the ground beneath our feet. It starts with the very design of our world.
Right, because the story of an earthquake, it doesn't begin with the shaking. It begins with the simple fact that our planet is anything but still.
I mean, just look at the Earth's surface. It's not some smooth, perfect marble. It's got these massive scars, right? Huge mountain ranges, deep ocean trenches. These aren't just random features. They're actually the seams of a giant, planetary-sized jigsaw puzzle.
And those puzzle pieces, we call them tectonic plates. The entire outer shell of our planet, the crust, is shattered into these enormous slabs of rock. And here's the kicker. They're not sitting still. They are constantly in motion, kind of floating and sliding over a hotter, gooier layer of the mantle below.
And you can see the results of that movement right here. Each one of those little red dots, that's an earthquake. And look, they aren't just scattered randomly across the globe. No way. They form these perfect outlines that trace the edges of the tectonic plates. This is where all the action is. It's where plates are grinding past each other, pulling apart, or smashing together.
Okay, so now we know where they happen, at the plate boundaries. But how do they build up enough energy to literally move mountains? See, it's not a nice, smooth process. It's more like a violent stick and slip.
And the key to understanding this is to know that faults are not smooth, greased-up surfaces. They're incredibly rough and jagged, with these little stuck patches called asperities. Think of them as high-friction spots that just lock the two sides of the fault together, even as the tectonic plates are trying their hardest to keep moving. So as the plates keep pushing against one of these locked asperities, the rock around it starts to bend and warp. It's just like bending this chopstick. It's not breaking, not yet. It's just storing up an incredible amount of energy. We call that elastic strain.
And this whole thing is called the stick-slip cycle. First up is the stick. The asperity holds on for dear life while that stress just builds and builds, sometimes for years or decades or even centuries. Then, the slip. The stress finally becomes too much for the asperity to handle, and it breaks. All that energy that was stored up gets released in an instant. And that release, that's the earthquake. It's the planet's version of that chopstick finally snapping.
Now that sudden, massive release of energy doesn't just stay in one place. It explodes outwards from the fault as these incredibly powerful vibrations that we call seismic waves.
And there are two main types of these waves that travel through the Earth. First to the finish line are the P waves, or primary waves. They're compressional, so they cause a kind of push-pull motion in the rock. They're the fastest, and they can travel through pretty much anything, solids and liquids. Right behind them are the S waves, or secondary waves. These are shear waves, and they create that classic up and down or side-to-side shaking. They're slower, and here's a really neat detail. They can only travel through solids. Now, that time gap between when the P wave hits and when the S wave hits is super important. It's exactly what seismologists use to figure out where an earthquake's epicenter is.
So how often does all this happen? Well, seismologists found a basic rule of thumb for earthquakes called the Gutenberg-Richter Law. Basically, it says there's a trade-off between how big an earthquake is and how often it happens. So, for every one massive magnitude 7 quake, you'll get about 10 magnitude 6s and 100 magnitude 5s and so on. The takeaway? The big ones are rare, thank goodness, but the small ones are happening constantly.
But, and this is a big but, that relationship isn't exactly the same everywhere on Earth. The precise ratio, what scientists call the B-value, actually changes depending on where you are. So out in the middle of the ocean where the crust is being pulled apart, you see tons of smaller quakes. But in subduction zones where one plate is diving underneath another, the B-value is lower. And what that means is those areas are way more likely to experience the really, really big ones.
Which, of course, brings us to the ultimate challenge, the million-dollar question. We get the mechanics, we understand the waves, we even know the frequency. But can we predict when the next big one is going to hit?
It's the question on absolutely everyone's mind whenever this topic comes up. And the answer? Well, it's a lot more complicated than a simple yes or no.
Okay, so we need to draw a really clear line here. On one hand, you have deterministic prediction. That's the dream, right? Getting a specific warning, a magnitude 7.2 will hit this city at this time. The problem is, the Earth's crust is just too chaotic for that right now.
So what we have is the reality, stochastic forecasting. Think of it less like a prediction and more like a weather forecast for the ground. It's all about calculating probabilities, like what's the likelihood of a certain size earthquake hitting a region over, say, the next 30 years.
And the good news is, these forecasts are getting better. We are making real progress. For instance, a recent model used in California showed a probability gain of 1.7. What that means is it was 1.7 times more accurate than the older methods. Now, it's not a crystal ball, but it's a huge step forward in really understanding and mapping out the risk.
And this quote from a leading seismologist really just sums up the whole modern approach. It's not about searching for some single magic clue that's going to tell us everything. It's about taking all the data we have, all the historical records, all the seismic readings, and plugging it into really smart models to actually quantify the risk.
So that leaves us with one last really important question. If we can't have perfect prediction, what are we supposed to do? Well, the answer is to shift our whole focus from prediction to preparations. It means we use these probability maps to build smarter buildings, to create better emergency plans, and to become more resilient, so we can live and even thrive on our incredible, dynamic, and very restless planet.